All right, so the next speaker is Ulpu Remes from University of Helsinki.
Thank you. So I'm here to present this joint work on using multi-fidelity data in Bayesian optimization for atomistic structure search. And the plan for this presentation is that I first talk about what we wanted to do in this work, and then I have some method details and some results. And I wanted to start with the structure search task considered in this presentation. So we have this alanine molecule, and here we focus on the 4 rotatable bonds that are marked in the picture. And the idea is that we fix everything else about the molecule structure, and then we find the rotations that minimize the potential energy of the molecule. So this is an optimization task, but we don't know how the potential energy behaves with respect to the rotations, so we don't have a function to optimize. Instead, we can map the rotations to these molecule structures, and then there are energy calculation methods that we can use to calculate the potential energy based on the structure. So essentially, our task is to minimize an unknown target function based on point evaluations like this. And as discussed in several previous presentations also, we can solve this problem with Bayesian optimization. And just as a quick reminder, the key components in this optimization method are the model that represents what we know about the unknown target function, and the acquisition rule that, based on this model, decides which input parameter combinations to evaluate. So this is an iterative process where we start with some initialization data, and then we iterate between model updates and new acquisitions. And our aim is to use as few evaluations as possible to find the input parameters that minimize our unknown target function. And what's special about our optimization task is that there are actually several energy calculation methods, and these have varying accuracies, and also the more accurate methods tend to be more expensive in the sense that the calculations take more time. And in the past, we would have chosen one method to run all the evaluations with, but now we wanted to explore using several methods at the same time, so that optimization can benefit from the cheaper evaluations while it searches for the rotations that minimize the energy calculated with an accurate and expensive method. And this is what we understand with multi-fidelity optimization. And to be clear about our motivation, we want to solve an optimization task, and we want to do that in the least possible time. And there's a limit to how much we can reduce the evaluation count because optimization needs to explore. So we do need to run evaluations with various inputs. But when we think about it, we don't need for all those evaluations to be accurate. For example, when we have a minimization task, we don't need precise information about the large values. So we could well calculate those ones with an approximate method and reserve our accurate and expensive evaluations for the kind of the small values that matter for our optimization task. So provided that there is correlation between our approximate and accurate method, so that a large approximate value implies a large accurate value, we should be able to use an approximate method to explore and to narrow down the search space and to save time. And sometimes when we want to save time, in optimization, we say that we want to accelerate optimization. So here we could say that the reason we're interested in multi-fidelity optimization is that we want to use a correlation between these energy calculation methods to accelerate Bayesian optimization. And in this study, we look at two approaches, but now I have to mention that now when we talk about these unknown functions associated with the different energy calculation methods, we call those tasks, and we separate between the target task that we want to minimize and the support tasks that we use as auxiliary information sources. I hope that is clear. And then about these two approaches, first, we wanted to look into using support task data to initialize our target optimization task. So here we start with a support task optimization run. We use that to collect data, and then we use that data as initialization data in a separate target optimization run. And here, this target optimization uses a multitask model to capture dependencies between the tasks and to transfer information from the support task data to the current optimization task. But otherwise, it's like standard Bayesian optimization, and we only use one task at a time here. But we also looked into, or wanted to test multitask optimization, where the optimization uses a multitask model and also a multitask acquisition rule. So the optimization can choose both which input parameters to use and which task to use in its evaluation. So that was what we do in this work. And next, I'll introduce the model and the acquisition rules that we used, and then the results. So about the model, like most works, we use Gaussian process regression, where the important feature is that the distribution over an unobserved output value conditioned on the available observations is a normal distribution with mean and variance that we can calculate based on information available in the model. So essentially, this framework provides us predictions and uncertainties in a convenient format. And also, we essentially use the same model with single task and multitask data, because in this Gaussian process framework, the task is modeled as an additional input parameter. So the X here on the slide, it can be the rotations T, or it can be the rotations T and the task I. And really the only difference between modeling single task and multitask data is the covariance function, which we choose when we set up the model. And here are the covariance functions that we used in this study. So when we had a single task data where the input is the rotations, we used a standard periodic kernel. And then when we had multitask data, we used this separable construction where we have a base kernel K from the single task case combined with this co-regionalization kernel B. And this co-regionalization kernel should capture correlation or covariance between the tasks. And this construction is known as intrinsic co-regionalization model. And also both these kernels are standard choices. Then about the acquisition rule, when we do single task optimization, we use this ELCB or exploratory lower confidence bound acquisition rule. And we use that because it has worked well in previous studies. And as for the multitask case, then we need our acquisition rule to choose both the rotations and the task. And we also need to take into account the cost associated with each task. And in this study, we used this simple two-step process where we first choose the rotations by fixing the task to the task that we want to minimize, and using the ELCB scores from the previous slide. Using those to choose the rotations. And then we fix the rotations, and we look at the posterior predictive distribution over tasks, and choose and check how much observing each task would reduce the target variance. And then we compare the tasks based on variance reduction divided by cost. So we try to choose the task that would maximize the target variance reduction to cost ratio. So that was the Bayesian optimization setup. And now I try to squeeze in some evaluation and results. So as I said in the beginning, we evaluate this method with the alanine example, and we used 3 energy calculation methods from the least accurate to most accurate. We had AMBER, and when we use that, one evaluation takes 0.3 seconds. And then we had 2 methods that use this FHI AIMS, and these took 23 seconds and 56 seconds. And now our aim is to find the rotations that minimize energies calculated with this most expensive method, E2. And also when we do multitask optimization, we use these computation times as the costs. But we start with baseline optimization. So here we did all evaluations with the E2 energy calculation. And we initialized optimization with 5 random observations, and we ran 20 repeats. And if we look at this best observed energy value with respect to iteration, we can see that there's variation between the optimization runs, but also all of them converge to the same energy level. And so to compare optimization methods, we chose a threshold value, and then we looked at how many iterations or how much time it takes until optimization converges so that we observe an energy below this value. And for example, in this baseline case, it took between 125 to 200 iterations. And we represent those results with standard box plots. And our first comparison is between baseline optimization and the multi-fidelity method, where we initialized a target optimization run with some support task data. And here we collected 155 support task observations, and we initialized the target optimization with those, plus 5 target observations. And looking at the results, we see that initialization with the support task data reduces the number of iterations in the target optimization task. So the optimization finds the minimum faster, especially when we initialize with this E1 data. And that's because this E1 and E2 energy kind of surfaces, they actually have the minimum in the same location in the rotations search space. However, we also observe a reduction when we use E0 data. And also, we are really interested in the reduction in the total computation time. And when we look into that, we have to take into account also how much time we spent on the support task optimization run. And when we take that into account and look at the computation time, the difference between using E0 and E1 disappears a bit. And actually both methods reduce the time to convergence about 50%. So that's what we achieved with this method. And now we can look at the other one. So here we compare baseline optimization to multitask optimization. And we initialize this multitask optimization runs also with 5 observations from each task. And we observe again that using multi-fidelity data reduces the computation time. And here we can see that we get the best results when we use both E0 and E1 task as the support tasks. And in that case, the reduction is around 75% from around 160 minutes to 40 minutes, so around 2 hours reduction in the median computation time. So to summarize, we evaluated these multi-fidelity optimization approaches with this alanine as an example task. We compared 2 approaches and we saw that both were able to reduce the total optimization time. And I just quickly wanted to mention that in this study, we used EmuKit to run Bayesian optimization, but since the results were so positive, we're now also implementing this multi-fidelity capabilities in our software package BOSS. Sorry for going over time.
No worries. Yeah, thank you. It was nice to see so impressive results on the reductions of time needed. So questions from the audience? Multiple?
Thanks for the nice talk. Ulpu, can you remind me, does it again work with the support task, the heuristic? How do you choose which support task to use? Like
yeah, that's where I panicked, I think. So in the heuristic, we choose the rotations based on the target task. So we always look at the target task and we look at which rotations we would choose if we were doing baseline optimization. And then which task to use in the evaluation. This can be either the target task or the support task. So we look at those equally. And we kind of consider if we run the evaluation with this or this or this task, how much would that reduce the variance in the target task predictive distribution that we calculated based on our current model. And of course, observing the target task itself, that would reduce the variance the most. The variance would disappear because we observed the task. But if there's correlations between different tasks, also observing something else will reduce the variance to some extent. And so that's why we calculate these variance reductions and then we divide them by cost. And that's what we use as the criterion for choosing which task to use.
I think I didn't understand whether, or the minimum energy structure, was that found with all 3 different methods?
Yes, because at least we assume so. So here we assume, based on evaluations carried out in previous studies, that the baseline optimization would find the minimum energy structure. And we saw that all the baseline runs, when we ran it 20 times, they found the same structure. So we assume that was the minimum energy structure. It's just that there's small differences. So that's why we used this threshold. And we were just checking that how long does it take for the optimization method to converge? So how long does it take for it to find this minimum energy structure up to some tolerance? And so, yeah, we were expecting that we always find it, and we're just checking how many iterations it takes or how long does it take to find that. There was one exception. When we were using this running multitask optimization and using E0 as a support task data. And when we repeated that optimization 20 times, there was one run that was not able to find the minimum energy confirmer, at least within these 200 minutes that we had allocated for each optimization run.
And in this figure, why didn't you include the E2 data?
So in this figure, this blue one is the baseline. So that's only doing evaluations with E2. And these ones are doing multitask optimization. So they are trying to optimize E2, and they succeed in optimization, they succeed in that because the evaluation criterion is when do we observe an E2 value that is below the threshold. So the other tasks are just support tasks. We don't really care what we observe about those. We just use them as an auxiliary information source for the E2 optimization. So all of these are trying to optimize E2, and we don't see E2 here because what we're listing here is which method we're using as the auxiliary information source. So we were using either one of the cheaper methods or both of the cheaper methods.
Okay, thank you.
All right, let's thank Ulpu once more.